Okay, so for those of you who missed the lecture, I think it's really good that we're having this opportunity to go over things now. So the lecture 5 was on measures of variability. And as we mentioned, measures or descriptive statistics come in two forms: measures of central tendency and measures of variability. So measures of central tendency look how scores come together. Measures of variability look at scores, how they spread apart. So a definition that I could give you for variability are looks at the spread or scatter of the scores in a distribution. So the lowest possible variability is zero, or the minimum possible variability is zero. And how do we get that? That occurs when all of the scores are the same. So if we were to look at a distribution, let's say all of the numbers were 3. 3, 3, 3, 3. So add that up. 3 plus 3 plus 3 plus 3 is 12. Divided by 4 equals 3, right? So if I were to subtract the mean or the average from each of these, or all of them individually even, 3 minus 3 would be 0. And the variability for all of them would be 0, in which we could say that there's no variability whatsoever. But most of the time that doesn't occur, that everyone gets the same score. So we have to find ways to measure variability. So if we look at a distribution and even the scores differ, as long as they differ to some degree, we have variability. Okay, now let's apply it. So let's say we gave a test, and a test average was, say, a 75. An individual scored a 75, and the test average was a 65. That's a better way of saying it. So everyone had their spread of scores, and 65 was the average, but you got a 75. So how did you do? Did you do well? Did you do poorly? In this situation where all of the scores are clustered together, tightly clustered, then getting a 75 is more meaningful and it might be significant. So if the range of scores, or two standard deviations was something like, I don't know, let's say 71, and you're above two standard deviations with your 75, then that's significant. But let's say the spread of scores was really, really wide or really dispersed, then we have something called high variability. And in such a case, the wide spread of scores may be less significant. So if two standard deviations above the mean, you got something like a 95. Well, getting a 75 is no longer that impressive. You see? So if two standard deviations above the mean was 71, it's very good. If it's 95, then it falls within the normal expectation. So, getting a 75 and the average was a 65, ultimately, its significance will depend on how tightly clustered or widely dispersed they are. Now, another example would be in sports, right? So if you have two basketball players and they average 20 points, right? Are the two players the same? The answer is no, because one player might have a range between 18 to 22, and the other player might have a range between 10 and 30 points. So if I were to ask you which player is more consistent, you would probably pick the player that scores between 18 to 22 points, right? And that they're consistent because there's very little variability. Now, the player who scores 10 to 30 points, they're less consistent, and therefore that high variability results in less significance. Okay. So another example, psychology or Another issue is psychology. Most factors are on a normal distribution, and the job of a psychologist is to try and understand or explain variability. So notice how I talked about two standard deviations above the mean or below the mean, because what's considered normal or atypical is usually about two standard deviations above or below. All right, so our job is to interpret it. And statistical inference is, it's going to be harder when there's more variability. So the more variable a phenomena is, the less precise the estimate you can get about the population's location from a sample. So we need to find a way to summarize variability, and let's start. So when we look at measures of variability, the first measure we could look at is something called the range. And the range is analogous to the mode. What do I mean by that? The mode was the roughest estimate or the crudest estimate of, central tendency. So if the mode is the crude measure or roughest estimate of central tendency, the range would be a rough estimate of variability. So when we look at the range, the definition of range is the highest score minus the lowest score, or you might hear it said the distance between the highest and lowest score. And most people use that as the understanding, but there are others who refer to the range as the highest minus lowest plus 1. And we've done that before when we looked at interval size. And one of the issues with interval size is that it ignored one of the scores. It ignored one of the data points. So some people think the range should be highest minus lowest in parenthesis plus 1. So let's take an example. Let's say the class average range between a 90 and 100. What's the range? Ultimately, you could argue two positions. The first position you could argue is that the range is 10, right? Because 100 minus 90 is 10. But other people say, well, 90 is a score. That's something people got. And 100 is a score. That's some people got that score. So we have to look at both endpoints. And what the second formula of highest minus lowest plus 1 does is it includes it, or both scores. So in this case, we would do 100 minus 90 in parenthesis is 10 plus 1 is 11. Does this make sense? Yes, no? Okay. So that's how you would calculate a range. You need to know for the test both conceptually and mathematically how to process a range, right? So conceptually, it's just the difference between highest and the lowest. Formulaically or mathematically, it would be either h minus L or h minus L plus 1. Okay. Very important to understand that the range is a rough estimate of variability, and it can be misleading because if you have one extreme score, the range goes up notably. So we need to make it tighter. We need to, control for some of this. So let's take a look at other measures. So there's something called the interquartile range. Now the interquartile range is the distance between the 75th percentile and the 25th percentile. Notice we're no longer looking at the highest and the lowest, because the lowest would be the first percentile or 0 percentile, and the highest would be the 100th percentile or 99th percentile, depending on who you ask. So that would be a wide range. What we're doing is we're bringing it to the quartiles, 25th to 75th percentile. Now, you can calculate percentiles, or you could calculate a raw score, knowing a percentile the same way we taught it in chapters 3 and chapters 4, right? So look back to that. But for the sake of argument, let's make up. Let's say a person can get anywhere from a 0 to 20 on a quiz. 0 being nothing 20 is 100. And the 25th percentile was 6, a score of 6. Again, I'm making this up. And the 75th percentile was 14, right? What would the interquartile range be? So what you would do is you would say 75th percentile, right? 14, and then 25th percentile minus 6. 14 minus 6 is 8. So all of a sudden we have 8 units of variability. You see how that would work? We figure out 75th percentile and subtract the 25th percentile from it, and that gives you a nice spread of the middle 50% of scores, right? How can I prove to you that that's your middle 50%? What's 75 minus 25? So that's percent in the middle of 50. And by doing the interquartile range, it's less sensitive to extreme scores, right? Because we may have gotten one really wacky score and then the range was set off. So the interquartile range is better than the standard range. Now, watch this. We can even get more sensitive, and this is what we call the semi-interquartile range. So in the semi-interquartile range, we're doing the same thing we did and just dividing it by 2. So the semi-interquartile range is 75th percentile minus 25th percentile divided by 2. So let's take the example I gave you, right? So 14 on that quiz was your 75th percentile, minus 6, that was your 25th percentile, equals 8. 8 divided by 2 is 4, right? So with that fictitious numbers that I gave you, your interquartile range would be 8, and a semi-interquartile range would be 4. Make sense? Okay. And what's nice about the semi-interquartile range is that it's not affected by extreme scores, right? So the most affected would be the range as a whole, because it takes all the way from one extreme to the other. So 0 to 20, we would say that that's 20 units of variance, or 21 units of variance, depending on how you calculate it. The interquartile range, because I made up numbers, we had a interquartile range of 8. The semi-interquartile range, we had a semi-interquartile range of 4. And if you listen to this, notice how the number, as we get more careful with our calculation, gets more truncated, gets smaller. Okay, make sense? So semi-interquartile range is useful, and it provides typical variability from the median. Now, it's interesting that the midpoint, if we look at it, is the 50th percentile. So 50th percentile was the median. So semi-interquartile range is a similar statistic of variability that the median would give us for central tendency. I hope that helps. Okay. So the next thing I want to introduce you to is variability, right? Like I said, variability was the difference between each score from one another, and each, whatever. Variability is the spread of scores, how scores differ from one another. Now, deviation and variability is a little bit different. Variability looks at how each score varies from one another as a whole. Deviation looks at how scores differ from a middle number. And the most common middle number or score of central tendency we look at is the mean. So a deviation score would be x minus x bar, right? So x minus x bar is the deviation of an individual score from the mean. Now, if we add up that column, we have the sum of x minus x bar, and that is always equal to 0. I showed you that last week, so there's no earth-shattering information there. And I will show that to you again a little bit later. Okay? Now, mean deviations. Here's a way to avoid having to square units. And we're going to talk about variance and why we have to square units. But there might be a way to avoid squaring units. So the sum of x minus x bar, or in this case I use the sum of x minus mu divided by n, would be mean deviation scores. Okay? And doing this, you'll notice that it's the absolute value of x minus x bar, or x minus mu. That is important because if you do sum of x minus x bar, it's always 0. So because the negative numbers cancel out the positive numbers. In this case, all we get are positive numbers. So the negative numbers are then converted into a positive number. All right, so we drop the sign. And this circumvents, like I said, the process of squaring deviations, and it's pretty good descriptive statistic, but it's not precise. And that is to say that smaller deviations are observed when calculating them from the median than the mean. So typically we look at x minus x bar, each score, how it differs from the mean. If we look at the median, we're going to get smaller deviations. And that's to be expected because we said that the mean is sensitive to extreme scores. The median is not. Okay. So you're going to have smaller deviations as well. All right, so variance. So variance looks at the average variability from the mean in squared deviation units. So far we've had x minus x bar. Now, if we do x minus x bar, or x minus the mean, and we add that up, we always get 0, right? But when we square it, negative numbers become a positive. So negative 3 times negative 3 equals a positive 9. And if we add up that column of squared units, we get something called the sum of squares, or SS. There is a population estimate and there is a sample estimate. So you'll see the population estimate for variance has the lowercase sigma with a squared unit, and in a sample it has just the letter S italicized squared, and so that's how we would do it. Now you'll notice that because a sample is smaller than a population, we have to have a more conservative estimate. And in order to make sure that our scores are a conservative estimate, we actually do n minus 1. And so we take one participant away from the total number of participants. And that's helpful in increasing variance. So whatever we would have calculated the variance to be, in a sample, the variance is going to be higher than in a population, and you're going to see that when I crunch the numbers for you. So what's the formula? The formula for variance is the sum of squares divided by n, right? And in a sample, it's the sum of squares divided by n minus 1. As I said, n would be the total number, and in a sample we want it to be conservative, so we take one participant off. Okay, and so these are our formulas. So SS is an abbreviation of adding all the scores and subtracting them from the mean, and then squaring each one. Variance takes this sum and divides by your degrees of freedom. Remember the buzzword degrees of freedom, right? Because in a sample we say it's n minus 1, so degrees of freedom are also n minus 1. All right, and then standard deviation, we're going to take the square root of the variance, and then that's that. Okay, now here's our data set. I'm going to actually march you through the data set by hand. So I'm going to stop the video and then I'm going to put all the numbers on the board and start with that. Okay, so let's stop this. Oh, actually, you know what? 1 second. I may want to say one more thing. Let's talk about the properties of standard deviation before I show you. So the properties of standard deviation, again, if a constant is added or subtracted from it, every score in a distribution, if you add a constant from it, the standard deviation will not be changed. You know, it's interesting, when we talked about the mean, right, we said if we add or subtract something to the mean is increased or decreased by that constant. When it comes to standard deviation, the standard deviation is unchanged if we add or subtract a constant to it. Why? Because we're looking at spread of scores. All we did was shift the whole distribution up. So that's important. Okay. And the next thing is, if every score is multiplied or divided by a constant, this standard deviation will be multiplied or divided by a constant that is consistent with what we said with the mean. Okay. Now, the standard deviation from the mean will be smaller than the standard deviation from any other point in a distribution. That's an assumption. It's not always met out, but typically we say that the standard deviation, if we look at it from the center point, and the mean is typically the best center point, it's going to be smaller than, let's say, looking at the 5th percentile and the 95th percentile, right? Because the central point is much different. All right, so that's the lecture. I'm gonna stop there, and then I'm gonna reopen it with a chalkboard lecture. Okay, so I figured the best way to do this lecture, and particularly for those of you whom I wasn't teaching because I was in Washington, D.C., I figured it's best to record myself giving the lecture, and that could be useful if you had any questions, or perhaps my colleague did not teach it the same way as I would. Okay, so what you have here is the same data set we worked with in the last class when we calculated the mean, median, mode. And let's say we wanted to look at motivation. And these were ratings of motivation or self-motivation, right? So these are motivation scores, right? So X is always a score. Motivation, these are motivation scores, right? Now, we added up the column, and we get 44. So if you remember, to calculate mean, your mean is the sum of X divided by N. So in this case, our mean is equal to 44 divided by 11, which is equal to a mean of 4, right? Because if you add this column, the top number, the sum of X is 44 divided by 11 scores, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That gets us 4. Now, what the next column is called the sum of deviations. And if you may remember from last class, the sum of deviations is always equal to 0. So let's see what happens. 1 being X minus 4, so 1 minus 4 equals negative 3. 2 minus 4 is equal to negative 2. 3 minus 4 equals negative 1. 3 minus 4 equals negative 1. 4 minus 4 equals 0. 4 minus 4, 0. 4 minus 4 equals 0. 5 minus 4 equals 1. 5 minus 4 equals 1. 6 minus 4 equals 2. And 7 minus 4 equals 3. So if we add up -3 plus -2, we get -5 plus 1, or -1 is -6, -7. Plus 0 is -7, -7, -7, -6, -5, -3, 0. So if you add up these columns, you will always get to 0. So the sum of deviations, which is x minus x bar, is always 0. Okay. The sum of squares, this is called SS, or the sum of squares, is not always equal to 0. So -3 times -3 is 9, 4, 1, 1, 0, 0, 0, 1, 1, 4, 9. Now, the sum of squares in this case is 13, 14, 15, 16, 17, 21, 30. So we get a sum of squares of 30. Okay. Now, this is going to be important when we get to the computation piece. If you look on this side, I've given you 4 formulas consistent with the slides, and they're all formulas for variance. Now, how do you know they're formulas for variance? Variance is always used with squared. So you'll notice, sorry for getting out of the screen, variance is always in squared units, so I circled the squares. Okay. Now, we'll go through it. So let's take our definitional formulas for variance for a population and variance for a sample. Let's work through it and see what we get. Okay. In the definitional formula, we said it's a sum of x minus x bar, or the sum of squares. We get here's the same formula, I'm just working over here, is the sum of x minus x bar squared over n. Now, what was the sum of x minus x bar? So the sum of x minus x bar was 30. And the n, what was the n? The n was still 11. So if we were looking at a population variance, sorry, I don't know why this is doing that. If we were to look at a population variance, we would calculate it as follows. We would say 30 divided by 11 equals 2.727. 2.727. Now, one of the things we said about sample variances, our sample variances are a little bit more conservative, because when you don't have all of the participants of interest, you want to be more conservative. You want to make sure that the true population is found or in your sample. So a sample variance is always going to be higher than a population variance, and I'll show you. So the definitional formula for a sample variance was the sum of x minus x bar squared over n minus 1. So what's our change in formula? This time we have that minus 1. So that you're going to see is going to add variance. Okay, so our sum of squares. What was our sum of squares? Sum of squares is 30. So let's put 30 there. Now, the n was what? We said the n was 11. What's n minus 1? That will be 11 minus 1, which is equal to 10. So 30 divided by 10 gives you a variance of 3.000. Okay, so notice our population variance is 2.727. And notice our sample variance is 3.000, or 3. Now, one thing you're going to see if we go back to this side of the board is that the definitional formulas and the computational formulas should come to the same numbers. And the computational formulas actually take more work to conceptualize, and that I'm going to work you through. So for the computational formulas, we need a sum of x column, and we need an x squared column. You'll notice that I didn't do the x squared column because I waited until we're doing computational formulas. So the x is 1. What's 1 squared? 1 squared is still 1. 2x is 4. 3 is going to be 9. Again, 9. 4 is going to be 16. Again, 16. Again, 16. 5 squared is going to be 25. 5 squared is going to be 25 again. 6 squared is going to be 36. And 7 squared is going to be 49. Now, if you could take some time to add that up, hopefully you'll get to the same numbers I do. So my numbers come up to 206. I just don't want us to go into screensaver. So 206. And because I don't have you fact checking my numbers, I'm going to do it one more time. And that's also helpful for those of you who are crunching the numbers a little slowly. So 1 plus 4 plus 9 plus 9 plus 16 plus 16 plus 16 plus 25 plus 25 plus 36 plus 49 equals 206. I got it twice, so I know that's correct. Now, as I notice, how did I get these numbers? I took the x column and squared it. So 1 squared equals 2 squared equals 3 squared equals 3 squared equals 4 squared equals 4 squared equals 4 squared equals 5 squared equals 5 squared equals 6 squared equals, and 7 squared equals. So I'm taking the x column and squaring it, and if you do that, you should get 206. All right. So I'm going to rewrite the formula because it's good practice to rewrite your formulas. So let me take this eraser, and I'm going to restate our formulas. Write down these numbers because with the definitional formula, we got 2.727 and 3.0. Okay, so I'm going to erase this. And with the computational formula, I should get the same numbers. Okay, here it goes. So our computational formula is 1 over n and then brackets. Whenever you have brackets, brackets are the same as parentheses. Work inside the brackets first. Okay. And then we have the sum of x squared, right, minus the sum of x square that value over n. Now, the only difference between a sample and a population was what? The relative conservative nature. Always, when we look at a sample, always you'll see that it's n minus 1. Okay, so let's work through the formula. The formula is 1 divided by n minus 1 times the sum of x squared minus the sum of x, square that over n. Okay, so let's work through it. So with the first one, we're going to say population variance. 1 over n is 1 over 11, right? Because n is always 11. It's remained 11. And we're going to start plugging in these numbers. So what was the sum of the x squared column? The sum of the x squared column was 206. So we're going to do 206 minus, what was the sum of x column? What was the sum of x column? It keeps freezing on me. The sum of the x column was 44, so minus 44 squared over 11. Okay, so let's work through this. The first thing you're going to need to do is get your numerator. So what would 44 squared be? That's not a problem. We just do 44 times 44, or you could actually square it, and we're going to get 1 over 11 times 206 minus 1936 divided by 11. You see how I got 1936? 1936 is that 44 squared. Okay. So now let's keep carrying our 1 over 11. We have our 206 minus, what's this part? So we do 1936 divided by 11. So we're going to work this part out. A 1936 divided by 11 is equal to 176. So now we have 1/11 times 206 minus 176. So 206 minus 176 equals 30. So we get 1/11 times 30. Now, what's 1/11 times 30? What do you get? When you do this, you get a number of 2.727. If that number sounds familiar, you're in a good place, because whether we look at a definitional formula or whether we look at a computational formula, the numbers will be the same. So on your homework, which I'm going to upload on Blackboard, as well as on the test, which will match it, your numbers for definitional and computational formulas should be identical. Does that make sense? Good. I'm assuming it did. Now, so that was our formula for variance of a population. Let's now work through just variance for a sample. All right. So variance for a sample, right? We know it's a sample because we're using Arabic letters, and by Arabic I mean English letters, right? So we're going to have s squared is equal to 1 divided by n minus 1. N minus 1 would be, good, 1/10, right? Times what we got over here, the sum of x squared column. So here's the sum of the x squared column. You work it down and you get 206. So we have, once again, the 206 here. And the sum of x, square that, we still have that 44 squared, right? 44 squared divided by 11. So you'll notice here's a nice cheat code. I like to talk about cheat codes similar to this being gaming. You'll notice, come on, the computer is messing up. You'll notice that the inside of your brackets, whether we're with a population or whether we're with a sample, the inside of your bracket will be the same. There's only one modification, and it's n minus 1. And that makes a difference because, as we said, we're going to work through the problem. Always carry every part of the problem. 1/10 times the bracketed 206 minus 44 squared. Again, let's do it again. Everything should be manual. And if we do it manually, we come up with the same numbers. We know we're doing the right thing. So 44 squared, also known as 44 times 44, comes to 1936 divided by 11. And that's exactly what we got before, was 1936 divided by 11. So let's do that. 1936 divided by 11, we get 176. So 1936 divided by 11, we get 176. And just keeping your notes, you will see that if you play it back, 206 minus 176 is 1/10 times 30, and 1/10 of 30 is 3.000. And what I'm modeling for you, I know I could just say 3, but I'm modeling the fact that I want you to carry your formulas and computations a minimum of 3 decimal places when you get to the end. So I could say 3, but I'm saying 3.000 so that we have that. Okay. So I've taught you 4 formulas, and get this. When we look at standard deviation undoes all of what we needed to do to square our units, because the sum of deviations is always equal to 0, so we had to square it to get the sum of squares, right? But we don't really want to report in square deviation units. We want to report in actual units. So if you look over at the formulas, I'm going to make some modifications. If I take a squared value and I take the square root of that value, what happens to it? It undoes the squared nature of it, and it becomes actual units. So watch what I do. For standard deviation, I'm going to erase all of the squares, right? I'm going to erase it. And I'm just going to add a square root sign to all of my formulas. Okay, that's all I'm doing. I'm adding a square root sign to my formulas. So now I have actual units. So if I were to do that over here, what would this sample standard deviation be? We take the square root of 3.000. Does anyone know what the square root of 3.00 is? So let's crunch that. If you got 1.732, you are correct. So the square root of 3 is 1.732. Okay. Now, that was standard deviation for a sample. If you go back, when I crunch the numbers for a population, we might want to get the standard deviation for that. Now, I'm not going to redo the whole formula. I think it's best to just take the square root of the value. So for a population variance, we got what? What was the population variance? It was 2.727. So you may remember that. So now, if I want the population standard deviation, and you know you're working in population because you'll see the Greek letters. So what I would do is I would take the square root of 2.727, And let me clear it. It didn't work. 1 second. I should be working on my calculator. 2.727. And then I square that value. I get 1.651. Okay. So in a nutshell, that's how we get to it. Perhaps we'll pause, we'll process the information, and I'll give you the extended form for standard deviation again. So let's stop here. We'll rework everything and go there. Okay? If you have any questions, feel free to email me. Thanks a lot.